Welcome to the lecture entitled Scientific Methodology, Paradigms and Puzzle Solving. I'm Andrew Chapman. In this lecture, we'll cover 6 topics. 1. The move from demarcation to methodology. 2. Popper's falsificationist methodology. 3. Philosophy, history, sociology, and psychology. 4. Normal science, paradigms, and paradigm shifts. 5. The implications for falsificationism. And 6. The implications for rationality and progress. Since science can't critically examine itself, that's the job of philosophy. Science isn't able to answer what is perhaps the most important question about itself, which is the question, what is science? Answering precisely and adequately the question of what science is requires finding some criterion, some standard or measure or benchmark that all things that are science meet and that all things that are non-science fail to meet. Such a criterion would demarcate or separate science from non-science. The search for a demarcation criterion, that is, for a standard that all science meets and that all non-science fails to meet, is at the heart of, and is the jumping-off point for, the history of the philosophy of science, as well as any systematic study of the philosophy of science. This search for a demarcation criterion is known as the demarcation problem. Finding a demarcation criterion whose foundations are plausible, that accurately separates fields into science and non-science, and that is possibly employable, has proven very difficult. 2 intuitive demarcation criteria, known as verifiability and falsifiability, quickly fall apart when they're examined closely. Verifiability, which rests the distinction between science and non-science on merely empirical criteria, cannot possibly be the demarcation criterion, as it makes science too empirical to the point that the criterion undermines itself. Falsifiability, which rests the distinction between science and non-science on the ability to possibly prove something false, cannot possibly be the demarcation criterion, as falsifiability itself is impossible. Nothing can be falsified via empirical evidence, as was shown by the Quine-Duhem thesis. Our reason for wanting a demarcation criterion in order to determine the essence or the nature of science is nonetheless an important issue and a worthy project. Fortunately for us, finding a demarcation criterion directly is not the only way to approach the issue of determining the essence or nature of science. The demarcation criterion, the issue of the correct scientific methodology, and the issue of what counts as progress in science are all bound up with one another such that a solution to any one of these issues reveals the essence or the nature of science and hence would be a solution to the other 2 issues as well. A demarcation criterion, a statement of the correct scientific methodology, or a statement of what it takes to make scientific progress are all just different ways of stating the same thing, which is what the essence or nature of science is. Since the central topic of this lecture is scientific methodology, it will help to understand what a scientific methodology is. A scientific method or methodology is an ordered set of steps, that is, a set of steps that need to go in a particular order, that a scientist ought to follow in order to achieve scientific answers to scientific questions and in order to make scientific progress. Notice that in this definition of a methodology, we have the term ought. A scientific methodology prescribes to a scientist how a scientist should behave. It's not a mere description of how scientists actually do behave, but instead is a normative claim about what sort of behavior when practicing science is good behavior. Since there are many different potential scientific methodologies, scientists and philosophers of science will need to determine which is the best methodology and whether perhaps different methodologies should be employed in different circumstances. We can rate a scientific methodology's merits according to 4 criteria. 1. Whether use of the methodology produces valuable results. 2. Whether the methodology is generally easy to employ. 3. Whether the methodology, at least somewhat, matches current scientific practice. And 4. Whether it is possible to employ the methodology. One of the most famous scientific methodologies comes from philosopher Karl Popper. Popper was a towering figure in the philosophy of science during the 20th century. He's best known for his theory of falsificationism, the theory that gave us both a demarcation criterion, falsifiability, and a scientific methodology, the falsificationist methodology. He was also a political philosopher, epistemologist, and philosopher of arithmetic, among many other things. While Popper's main target in creating his methodology was Karl Hempel's hypothetico-deductive scientific methodology, Popper nonetheless agrees with Hempel concerning Hempel's recognition of the creativity of science and his subsequent criticisms of a previously existing scientific methodology known as Baconian narrow inductivism. Baconian narrow inductivism was formulated by Francis Bacon. However, given the fact that scientific investigations don't change the truth of hypotheses, and given the problem of induction, Popper will not endorse any scientific methodology that claims either that induction is justified or that scientists ought to reason via induction. But both of those were central components of Hempel's hypothetico-deductive method. Since attempting to increase our confidence in hypotheses is either unjustifiable or impossible because of the nature of probability and the problem of induction, Popper thinks that we should instead attempt to decrease, in fact, entirely eliminate our confidence in our hypotheses. Our goal as good scientists, says Popper, is to falsify hypotheses. If we end up with evidence that fails to falsify a hypothesis, that doesn't confirm or increase the probability of that hypothesis. Sir Francis Bacon said that evidence that's in line with a hypothesis totally confirms the hypothesis. Karl Hempel said that evidence that's in line with a hypothesis increases the probability of that hypothesis. Popper says, no. It merely means that the hypothesis has yet to be falsified. That's not a positive status, it's just a neutral status. Popper calls this has yet to be falsified status corroboration, which contrasts with confirmation. Corroboration just means that the evidence so far is consistent with the hypothesis, but being consistent with a hypothesis doesn't show us anything positive about that hypothesis. Popper's falsificationist scientific methodology, when put in ordered steps, looks like this. 1. Observe the world and creatively decide on some problem that you'd like to solve. 2. Invent a hypothesis via some creative act of the imagination. 3. Decide which testable things are implied by the hypothesis. 4. Go out and collect some data that's relevant to the hypothesis and the test implications, keeping in mind that you should be trying your hardest to collect the data that has the best chance of contradicting your test implications. And then 5, see whether the data is in line with or not in line with your test implications. If your data is in line with your test implications, then your hypothesis is corroborated, but all that means is it hasn't been refuted. This isn't a positive status, it just means nothing has happened. Then you should get going on trying to refute your hypothesis by collecting more evidence that could possibly show that it's false. If your data is not in line with your test implications, then your hypothesis has been disconfirmed, says Popper, and scientific progress has been made. And then you should go back to step 2 and invent yourself a new hypothesis and keep going. Now, just a quick note on the possibility of falsificationism. Strictly speaking, it is impossible for empirical evidence ever to falsify a hypothesis. This is because, as the Quine-Duhem thesis shows, a false test implication only points to the falsity of something that's in an infinitely large set of propositions. Now, it might be that the falsity of the test implication is because the hypothesis is false, but since the set of propositions that the hypothesis is a member of is infinitely large, we'll never know for sure whether it's the hypothesis or something else that's caused the test implication to be false. And thus, strictly speaking, scientists can't set out to falsify hypotheses since they can't set out to do something that's impossible. However, we might still think that the spirit of Popper's methodology can survive the Quine-Duhem thesis. Good scientists, we could think, instead of searching for confirmations of their hypotheses, should search for evidence that is not in line with their hypotheses. While good scientists won't ever be able completely to falsify a hypothesis, data collection and experimental practices should still be carried out with a fully skeptical methodology and with an attempt to falsify. Enter Thomas Kuhn. Kuhn was a philosopher of science, a physicist, and a historian. His most famous treatise, known as The Structure of Scientific Revolutions, is perhaps the most famous and controversial work in the philosophy of science. The philosophy of science is unfortunately rife with theories about scientific methodology that were created by philosophers from the armchair. While it's true that it's philosophers and not scientists who are performing the supportive and critical work of the discipline of science, one might still think that it would be very difficult to perform the work of criticizing and supporting science if one didn't have some understanding of the everyday practices involved in scientific theorizing, data collection, and testing. The thought here is, then, that philosophers of science should either be scientists themselves or should be there looking at what actual practicing scientists are doing, before they try to invent theories of methodology or explanation or whatever else they might invent to criticize or support science. Of course, this isn't to say that scientists know more about science than philosophers do. To say something like that is a serious misunderstanding of the distinction between science and the philosophy of science. Scientists know how to practice science. Philosophers know how to understand and criticize science. What this is to say is that philosophers who study something X should at least take a look at what those who are practicing X are up to, even if those practitioners are totally wrong and misguided. Kuhn's philosophizing about science, then, starts from actually observing what practicing scientists are up to. His first step as a philosopher of science is to be a historian of science, a sociologist of science, and a psychologist of science. Kuhn would say that philosophizing can't even start before we do history, sociology, and psychology. The central methodological difference between philosophy on the one hand and history, sociology, and psychology on the other hand is that the evidence of philosophy is a priori or non-empirical, while the central evidence of history, sociology, and psychology is a posteriori or empirical. Philosophers are concerned with essences or natures, while historians, sociologists, and psychologists are concerned with the contingent facts that have occurred in the past or that are currently occurring in the present. When Kuhn observed practicing scientists, both in the present and in the history of science, he saw that the overwhelming majority of scientific practice looks like this. Step 1, presuppose, without argument or evidence, current scientific theory. And then, step 2, attempt to solve a puzzle that current scientific theory claims is solvable. Scientific theories come along with accepted research methods, standards of observation and measurement, a language, concepts, and even an accepted logic. All of these things are presupposed before the properly scientific work of experimenting or gathering data can even begin. The puzzle solving that results is what almost all scientists are up to nearly all of the time. Says Kuhn, in no usual sense, however, are the tests that scientists do directed to current theory. On the contrary, when engaged with a normal research program, the scientist must premise current theory as the rules of his game. So, experiments are not tests of the background theory, but tests of the experimenter's ingenuity at solving puzzles. So imagine, just as an analogy, that you're attempting to solve a jigsaw puzzle. If, after a while, you're not able to solve it, the proper conclusion isn't that there's something wrong with the puzzle, but that there's something wrong with you, that you're not brilliant enough to solve the puzzle. The thought here is that science can't possibly be a test of everything. A whole bunch of stuff needs to be presupposed, and what's presupposed is exactly what Kuhn says. The background scientific theory, the overarching pictures of the universe, the thoughts about what sorts of tools and methodologies and histories and research programs are acceptable. Only once we presuppose all of that stuff can we get working. So 99+% of what scientists are up to, says Kuhn, is puzzle-solving activity. Scientists presuppose the acceptable tools and the goal, and then they get working trying to reach that goal using those tools. This puzzle-solving activity is what Kuhn calls normal science. But how do scientists know what acceptable tools to use and what goal they are trying to reach? Where does the knowledge of these things come from? That knowledge, says Kuhn, comes from the paradigm that scientists are bound by. A paradigm in Kuhnian theory is an all-inclusive totalizing set of goals, research methods, standards of truth, rationality and observation, theories of explanation and interpretation, etc., that guides scientific research. Science is impossible outside of a paradigm, as outside of a paradigm, there are no goals or research methods or standards of truth, rationality and observation, theories of explanation and interpretation, etc. Thus, all normal science, meaning everything that scientists are up to 99+% of the time, this puzzle-solving activity is bound by paradigms. So normal science, the puzzle-solving activity, accounts for 99+% of what goes on with scientists and in science. Very rarely, however, all of a sudden, the paradigm that a researcher or that a whole set of researchers is in shifts such that it is a new paradigm that is guiding research. A paradigm shift is known as a scientific revolution or revolutionary science or extraordinary science. And paradigm shifts aren't technically science, since all science is bound by paradigms. Paradigm shifts instead look more like philosophy. Paradigm shifts are caused by non-rational historical, sociological, or psychological conditions. These conditions are non-rational, not irrational, but non-rational, in that they don't present reasons for the paradigm shift. They just cause the paradigm shift. Sometimes these non-rational conditions come in the form of anomalies within the current paradigm, which are feelings of dissatisfaction or unease with the current research program. However, anomalies are not reasons to get rid of the paradigm. As we'll see momentarily, there are no such things as reasons to get rid of a paradigm. Other times, these conditions that bring about paradigm shifts come in the form of, for example, changes in funding, changes in political conditions, the death of a towering figure in the field, etc. So paradigm shifts are caused, they aren't reasoned into. Paradigm shifts are non-rational. Again, not irrational. Irrational means out of line with rationality. Non-rational just means completely separate from rationality. These paradigm shifts are non-rational in that they are caused by historical, sociological, and psychological factors. But reasons aren't and can't be given for a paradigm shift to be made. Paradigms themselves are blind to the possibility of other paradigms. Thus, when scientists are working within a paradigm, it's not as though they can see other paradigms and can consider whether they want to shift over to those paradigms. They might see other theories, but insofar as a scientist can evaluate a different hypothesis or theory, that hypothesis or theory is still in their paradigm. The rules that are within a paradigm merely tell the scientist to just keep working on the problems and puzzles within that paradigm, to just keep using the rules and standards of that particular paradigm. So consider this analogy. You're working on a jigsaw puzzle. You know how to work on a jigsaw puzzle because of the rules of jigsaw puzzles and because there's a picture on the box that tells you what the goal is, what the final picture should be. But then you grow bored and you decide to switch to working on your Rubik's Cube instead. Now, a whole new set of rules guides your work. The jigsaw rules are gone. The Rubik's Cube rules come into play now. However, the switch that you made from the jigsaw puzzle to the Rubik's Cube, that wasn't guided by jigsaw rules or by Rubik's Cube rules. It was just guided by your own psychological state, your boredom. Jigsaw puzzle rules just tell you how to work on a jigsaw puzzle. Rubik's Cube rules just tell you how to work on a Rubik's Cube, and neither set of rules tells you to switch to working on the other thing. In fact, there are no Rubik's Cubes in the world of jigsaw puzzle rules, and there are no jigsaw puzzles in the world of Rubik's Cube rules. When a paradigm shift occurs, it's not as though new facts become available, so don't think of a paradigm shift like a scientific discovery. When paradigms shift, the old facts, the old data, those are seen in a different light. This is known as a Gestalt shift, and all at once seeing differently. So consider the famous duck-rabbit drawing. It's possible to see this as a duck. The bill of the duck is in the upper left-hand corner of the drawing. The duck's eye is in the lower right, and the back of the duck's head is to the farthest right of the drawing, and then the duck's neck is underneath all of that. But then it's also possible to shift your attention so that you can see it as a rabbit. When you see it as a rabbit, the upper left-hand corner, what you used to see as the duck's bill, now becomes the rabbit's ears. The eye stays the same, but what used to be the back of the duck's head is now the rabbit's nose and mouth, and the neck stays the same. This shift, when you see it as a duck, and then you shift to seeing it as a rabbit, and then you shift to seeing it as a duck again, is a real Gestalt shift. You can't see this drawing as both a duck and a rabbit at the same time. When you see it as one thing, it's impossible for you to see it as the other thing. Go ahead and try. Look at it as one thing or the other, and as you're doing that, without making a shift, see it as the other thing at the same time. This is how paradigm shifts work. Different paradigms are incommensurable with one another, meaning that when you're in one paradigm, you can't even see the possibility of another paradigm. Now, if it's true that 99+% of scientific practice is paradigm-bound, puzzle-solving normal science, then there are serious problems for Popper's falsificationist scientific methodology. Here are 3 of the most serious. First, what Popper calls falsification going out and finding evidence and overthrowing theory, is actually revolutionary science or extraordinary science in Kuhn's language. But since revolutionary science occurs very rarely, it can't be what is driving science. Scientists get to work every day. They do things. They make progress on what they're working on. But since paradigm shifts, revolutionary science, extraordinary science, only happens every once in a while, this can't be what we should be setting out to achieve. Second, what actually appears to be driving science is puzzle-solving activity, not attempting to prove some hypothesis or theory or paradigm false. And third, and here's perhaps the biggest problem, since paradigms are self-supporting, they tell scientists to keep on working on the puzzles they present. It's not even possible for a scientist to set out to overturn a paradigm. Even further, since paradigm shifts are the result of non-rational factors, nothing a scientist could set out to do could cause a paradigm shift. Paradigm shifts happen all on their own because of historical, psychological, sociological factors, not because anyone reasons their way into a paradigm shift. Thus, Kuhn would say to Popper, "What you are saying, Popper, drives science isn't." Now, Kuhn claims that all science is paradigm-bound and that only occasionally do these paradigms shift, and that the shifts are caused by non-rational factors. Thus, there are, it seems, serious negative implications for the notions of scientific rationality and scientific progress. According to Kuhn, scientists engage in the particular puzzle-solving activity they do, not because they have decided that these are the best puzzles to try to solve, but because their paradigm dictated that they solve those puzzles. Think about how scientists are educated. They go to a certain school, study with particular people, read out of particular textbooks, and all of this is part of the paradigm that they're being educated in. So they never had a chance outside of a paradigm to choose different puzzles or choose one paradigm over another. In fact, according to Kuhn, there is no outside of a paradigm where we could sit and choose between competing paradigms. That place doesn't exist. Further, scientists can never possibly see the world objectively on its own terms, but always merely through the lens of their own paradigm. And of course, it's not possible to compare the paradigm with reality to see whether the paradigm is getting it right, because then we would have to be at once outside of and in a paradigm to be able to compare the paradigm to the objective world, and this isn't possible. According to Kuhn, paradigm shifts don't improve science, they merely change it. And of course, if you think that science has been improving, well, of course you do, because you're bound by a paradigm that calls puzzle solving progress. Paradigm shifts couldn't possibly improve science since all standards of progress are bound up within paradigms. Thus, there is no paradigm-independent sense, no objective sense of the betterness of certain research projects over others. There is only paradigm-bound progress, all of which gets washed away in a paradigm shift. So Kuhn's theory can be somewhat complicated. Here are the main points. Paradigms are all-inclusive sets of standards and problems. All science is paradigm-bound puzzle-solving activity that Kuhn calls normal science. Very rarely, due to non-rational, again not irrational, non-rational forces, paradigms shift in what is known as a scientific revolution, revolutionary science, or extraordinary science. And don't confuse a paradigm shift with a scientific discovery. Discoveries occur within paradigms. Paradigm shifts are the non-rational dumping of scientists from one paradigm to another. Paradigm shifts are Gestalt shifts, such that paradigms are incommensurable with one another. They can't be compared with one another. You can't see one paradigm from within a different paradigm. Science is always practiced through the lens of a paradigm. That is, science is never merely objective. And finally, paradigm shifts can change science, but they can't progress science. In this lecture, we've looked at 6 topics. 1, the move from demarcation to methodology. 2, Popper's falsificationist methodology. 3, philosophy, history, sociology, and psychology. 4, normal science, paradigms, and paradigm shifts. 5, the implications for Popper's falsificationism. And 6, the implications for rationality and progress in science. Thank you.